Okay, I want to pick up um, sort of where we left off on unit 2. Now, the basis of the chemistry of aldehydes and ketones is the carbonyl group. Carbonyl group got double bonded oxygens instead of single bonded oxygen, like ethers and alcohols. They're still electronegative though, compared to carbon and hydrogen. They're just not as powerful. So when you compare them to hydrogen bonding, particularly, that hydrogen bonding OH group is very strong. That's why alcohols are so incredibly polar. But aldehydes and ketones are also polar, just not as polar as an alcohol. Now we're going to find in unit 3, acids are even more polar than alcohols. They're the most polar of all. Okay, as far as IMFs are concerned, you can see alcohols again are at the top, and aldehydes fall kind of in between the alkene and alkenes. And then ethers are sort of similar to aldehydes and ketones because of the oxygen. Okay, as we saw from unit 1, there are 3 different kinds of alcohol: primary, secondary, tertiary, and they can be oxidized or reduced. If they're oxidized, they're losing hydrogens. Tertiary alcohols don't have any hydrogens to lose. The aromatic version of the aldehyde, if you oxidize it, it turns into benzoic acid. Acetone, because it's got no hydrogens on that carbon, can be oxidized. So ketones cannot be oxidized, aldehydes can be, and that's one of the tests you're going to be using in lab this week. Now, the lab we're doing this week is on alcohols. Make sure you write up the correct one. Some people have written up lab 3, which is what we're doing next week, the soap lab. Okay, so in the middle test tube is a ketone, and the right-hand test tube is an aldehyde. So if we put an oxidizing agent in those 2 test tubes, the oxidizing agent's color will change if there's a reactant. And notice it changes on the right side, not the middle one. That means no oxidation occurred in the middle one, which was the ketone. Now we're going to be doing the same thing this week in lab. Now, there's been one substitution in the lab, and that's we aren't using chromic acid, and I'll talk about that in lab, because it was deemed a carcinogen. So we substituted it for another oxidizing agent. But this is very diagnostic. Will it oxidize? Yes or no? If it does oxidize, it's the aldehyde. Does not oxidize, it's a ketone. Now, this is where I stopped last time. This reaction you need to know. This and another one similar to it. We're using the same reaction when we talk about carbohydrates. Something called reducing sugar, and this is a test to determine that. Okay, so basically, we start with the aldehyde. we're going to put a oxidizing agent in there, and this is what happens. And it's also a alkaline or basic environment as well. Okay, so the first test is called the tolerance test. And what happens is the aldehyde goes to the salt of the acid. So you're looking at now what's going on whenever you have an oxidation, you have to have a corresponding reduction, no exceptions. Oxidation in 305 was the transfer of electrons or the loss of electrons. In 306, it's the loss of hydrogen. It's the same concept. It's just that in organic chemistry, we're looking at hydrogens leaving and coming rather than electrons. Okay, so if the aldehyde is being oxidized, what's being reduced? What's being reduced is the silver ion. And that silver ion is going to is going to gain an electron, in which case it becomes silver metal. So it's important to understand this reaction. Understand what's being oxidized, what's being reduced. The other one is called Benedict's reaction. And with Benedict's solution, you're oxidizing the aldehyde again, but you're reducing copper instead of silver. And this is the reaction we're going to be using in our labs. Is Benedict's, not Tollens. Tollens is classic. Benedict's is also classic and a lot cheaper because it's not silver to run. That's why we totally switched out Tollens. Up in Tacoma, we used to use Tollens anyway. And it's really a cool reaction. You end up with a silver mirror inside the test tube. In fact, that's how they refurbish antique mirrors. Antique mirrors had a coating of silver on the back, and when they get old, they either chip, particularly around the corners, and what they do, they make a Tollens reaction to plate out the silver on the glass. That's how they fixed it. Okay. So again, we're looking at something's being oxidized, aldehyde. Something has to be reduced. In this case, it's going to be the copper. So the copper goes from +2 to +1. And everything has moved over. Okay, so we've got aldehyde being oxidized to again, the acid salt. And the copper +2 goes to copper +1. Now, dadgummit. So when you look at this, oxygen's got a -2, and we have 2 coppers to balance off the -2. That means they have to be +1. So that's where the reduced copper is located inside that copper oxide. Okay, now there's some exceptions to this. If we have a dual ketone together with adjacent carbons, that will give a positive Benedict's test, even though it's a ketone. And the reason for that is there's an intermediate compound between these groups that is an aldehyde that ends up being oxidized. Same with if there's an adjacent hydroxyl group. Now we'll get this a lot in carbohydrates because if we look at glucose, glucose has something called a hemiacetal. Hemiacetals can open up to an aldehyde and a hydroxyl group, which is exactly one of the exceptions right here. So this particular reaction is very, very important in carbohydrates. Most stable form of a carbohydrate is a cyclic one, not a long string. So in your biology books, sometimes you see the glucose cyclic, sometimes you see it as opened up. They're both correct. One's more stable than the other. The cyclic one is more stable than the one that's opened up. Okay, so I'm going to hit this reaction hard when we talk about the carbohydrate part of this unit. Okay, so aldehydes and ketones can also be reduced to an alcohol. When the reduction happens, we're adding the hydrogen rather than taking it away. So this is a two-way street. You go from a three-carbon backbone aldehyde to a three-carbon backbone alcohol in a reductive environment. Whether it be an aldehyde or a ketone. Both of them can easily be reduced. Okay, this is the tricky part of this unit. What happens when you mix an aldehyde and an alcohol together? Something happens. What happens when you mix a ketone and an alcohol together? Something happens. They're called all these examples I have. So you're going to have four of these forms. When you have an alcohol plus an aldehyde, first thing that happens, you end up making a hemiacetal. A hemiacetal is the first part of that reaction. It continues on to form a full acetal. When we take a ketone, we form a hemiketal. And then the reaction goes on to a full-blown ketal. Now, the chemistry of aldehydes and ketones is the chemistry of carbohydrates. So you get these hemiacetals all the time in carbohydrates. Hemiketals, acetals. To form a polysaccharide, for example, small glucoses are strung together via an acetal reaction. So these reactions are very important. They're also tricky. So we're going to have two backbones. We're going to have a primary backbone, secondary backbone. Primary backbone comes from the aldehyde or the ketone. So if we look at aldehydes first, okay, the primary backbone again is the aldehyde. And that's, I've done it in yellow. That carbon that's attached to the aldehyde is called an anomeric carbon. You have to be able to identify the anomeric carbon. It is the root of this reaction. It's also the root of reactions in carbohydrates. That's the carbon that is opening and closing on glucose, for example, and fructose, and mannose, and all these sugars. It revolves around the anomeric carbon. So I always put a red dot by it. And that red dot is not going to change locations. It's going to stick with that carbon the whole way. All right. The first is the hemiacetal. Now, the carbonyl goes to an alcohol, an OH group. And the other part of the alcohol, this part gets stuck with an OCO configuration. So we've got OCO. So that's step number one when you're identifying these things is, where is the OCO? And then another alcohol, doesn't have to be the same one, it can be a different one. Carbohydrates, they're all different alcohols. In this chapter on aldehydes and ketones, they're going to be the same alcohol. But my point is, it doesn't have to be the same alcohol. It's just an alcohol. All right, when we add another alcohol, it attaches here on the OH group. It creates another OR. So here we have OCO again. Now notice there's no, the starting place in that aldehyde, there's no OCO. So that means it's not an aldehyde. Excuse me, it's not a acetal because there's no OCO, whether it be hemi or full acetal. We're going to find with the ketones, it's the same reaction. Only start with a ketone rather than aldehyde. Now I'm going to go through lots of examples of this reaction. Okay, so if we start with a ketone and an alcohol, we form the hemi version of that, which is called a hemi-ketal. So the ketal, ketone, acetal, aldehyde. Okay, so the first thing is, just like with a hemi-acetal, I'm going to form an OH intermediate. We add another alcohol, we're going to form the full-blown one. Now, both of these, again, have OCO. OCO. Now, I'm going to give you a test. You can test these. Is this an acetal or a ketal? It's a three-step process. I'm going to use it a whole bunch. Ketals also have secondary and primary backbone. And it also has an anomeric carbon as well. Anomeric carbon, again, is where the original carbonyl group was. Okay, so we have the alcohol attaching to the anomeric carbon, forming this OH group again, the hemi part, hemi-ketal. Okay, adding another alcohol, not necessarily the same one. It could be the same one or different ones. It doesn't matter, as long as it's an alcohol. And then we end up over here. Now, the difference between the two, the ketal and the acetal, has to do with the anomeric carbon. What's attached to the anomeric carbon? Is it another carbon or is it hydrogen? If it's hydrogen, that means you started with an aldehyde. If it's another carbon, that means you started with a ketone. Okay, so let's look at some examples now. These can also be cyclic. I'll talk at length about that as well. Okay, so here's the test. Let's look at the an example of one here. Okay, test number one. Is there an OCO present? Yes or no? If it's yes, then you are going to have an acetal, ketal, hemiacetal, or hemiketal, one of the four. If that's not present, then you don't have any of those. Okay, if it's present, the carbon in that OCO is the anomeric carbon. Step number two. Is there H attached to the anomeric carbon? Yes or no? If it's yes, that means it's a acetal. If it's no, it means it's a ketal. Now, it could be an hemiacetal or an acetal. Hemi means there's an OH present. So the next test is there an OH present on the anomeric carbon? If it's yes, that means it's a hemi. No means it's a full acetal or ketal. Okay, so let's apply the 3 steps to this guy over here. And by the way, on naming acetals and ketals, I'm not going to hold you responsible for naming them. They're kind of a pain to name, so we're just not going to do them out of the scope of this class. Okay, is there an OCO present in this molecule here? Yes. That means it's one of 4. One of the ketals or one of the acetals. Okay, is there an H present on that anomeric carbon? No. So that means it's some kind of a ketal then. Is there an OH? Yes, that means it's a hemiketal. All right. Let's do another one. So OCO, OCO, so that's a yes. That means the C is the anomeric carbon. Is there an H on the anomeric carbon? No. Okay, that means it's not a hemi. Actually, it means it's not an acetal. OH? No. Okay, so if there's no H there, that means it's some kind of ketal. And with no OH, that means it's not a hemi. So this is a ketal. Now these distinctions are really important when we get into carbs, because this allows you to determine whether the sugar is a reducing sugar or not. And it's a big deal in carbohydrate chemistry. Is this reducing sugar? Because they have whole different kinds of reactions with reducing sugars versus non-reducing sugars. This is the way you tell. Okay, so let's do another one. In fact, let's do let's do this. Let's start with that. Add to that a 3-carbon alcohol. And what does that create? Okay, first identify primary backbone, secondary backbone. Okay, so what happens is this carbon here attaches there. So this is going to be the anomeric carbon. So we'll repeat the primary backbone. And then we add in the first alcohol. And again, it attaches to the anomeric carbon. So what do we have now? And we're starting with a ketone here. So that means we're going to be creating a ketal. And what did we just create? Well, let's analyze it. OCO, yes. H present, no. OH present, yes. So this is a, with no H's attached to anomeric carbon, that means it's some kind of ketal. If OH is there, that means it's a hemi ketal. So the first step is always a hemi something. All right, let's add another another alcohol. So we're going to add another. Let's see, let's do this different. Propanol. And again, it's going to attach to the anomeric carbon. So we reproduce the backbone. Anomeric carbon stays the same. And there's our secondary backbone. Okay, let's analyze the OCO now. Okay, so OCO is a yes. Do we have H present? No, on the anomeric carbon. And is there an OH present on the anomeric carbon? No. So that means this is a ketal, full ketal. Now, when we get into carbs, we're doing exactly the same reaction. Carbs are structure-wise are more complex. So the reaction looks more complicated than it really is. So that's why you have to get really comfortable being able to diagnose these reactions. All right, let's do another one, only this time let's start with an aldehyde. Throw in an alcohol. Okay, so we have our two backbones. And what's going to happen is the alcohol is going to attach to the anomeric carbon, which is here. So the first step is going to be to create a hemi, because they're starting with an aldehyde, we're going to create a hemiacetal. We can verify that by doing our tests. So we go OCO, that's a yes. See, OCO. Okay, H, yes, and H is present now. It's right here. Is there an OH? Yes. So that means this is a hemiacetal. Now, hemiacetal or hemiketals are not all that stable. So what happens is typically the alcohol attaches again to the anomeric carbon. And there's still an H there. Okay, so let's do the analysis again. So we have OCO, a yes. H is a yes. H right here. And OH, no. So this means it's an acetal. So the intermediate step is a hemi whatever. You start with an aldehyde, it's a hemiacetal. You start with a ketone, it's a hemiketal. Again, this is the trickiest part as a unit right now, this series of reactions. Because the challenging part is we can have this happen in the same molecule if it's long enough. Think of a scorpion. A scorpion can bite itself if his tail is long enough. But same with these molecules. So if the molecule contains both an alcohol, an OH, and an aldehyde or a ketone, we can have the same reaction. It's just that everything's contained within the single molecule. We still got an anomeric carbon right here where the C is where the O is attached to the C. Now the molecule has to be at least 6 carbons long or longer. 6 carbons is kind of the ideal, most stable. It's because the bond angles are 105. 105 is the magic bond angle. Okay, and notice also it's an equilibrium. It opens and closes, opens and closes. The question is, which is more stable? Closed one is more stable. So it spends more time closed than open, but it always is opening. It's always exposing the aldehyde group or ketone group. Briefly, but it always exposes it. And then it slaps back down into the cyclic version, which is the most stable between the two. Okay, so let's look at an example. Let's take this guy. So this is going to be the anomeric carbon. And this tail now is going to attach to itself. Remember, the single bonds can freely turn. So now we have an aldehyde and an alcohol reaction, all in the same molecule. So what happens is this guy attaches there. So this is going to be the hemi acetyl. And that's starting to look a lot like glucose. Now we can do the same reaction again. We've got a hemiacetal. We can add another alcohol to it. So say we added propanol again. And that's going to attach to the anomeric carbon. That. So this would be the acetyl. Let's do our test. Okay, so we have OCO. We have H present. There's an H there. So that's a yes. And we have OH. Yes. So that's hemiacetal. We have OCO. H. Yes. And OH. No. So that makes that the acetal. Now your dry lab for unit 2 has lots of practice using this stuff. Now the interesting thing, you're hearing,
the alcohol. Add that on the alcohol. I see that that's the product, but you said it attaches to the carbon. But on the previous one, it had the OH on that same line.
But it still attaches to the atomeric carbon. Just other things are on your plus.
Okay, so it's like merging with it.
Yeah, well, more than merging, acid. That's true.
So instead of having like the two branches, it's just.
Well, everything converges on anomeric carbon. That's why I'm doing anomeric all over the place. That's where everything happens in these reactions. When you have an anomeric carbon with OCO, that's where the alcohol is attached to. First step, it attaches, but then it has an OH on there as well. Second step is the alcohol attaches, another alcohol attaches. The OH goes away and the alcohol replaces it.
Okay. Okay, so replace.
Yeah.
Okay.
And you still end up with 4 bond. The anomeric carbon has 4 bonds, so there's one here. So we have a CO bond, another CO bond. We have a carbon-carbon bond, and we have an H. And this is the anomeric carbon here. Now, a ketal does not, the 4th bond is another carbon, carbon-carbon. Did that help?
Yeah, I did.
Okay. And again, this is wild. That's why this unit 2 is kind of wild. This reaction is interesting, along with the oxidation reduction reaction as well. Okay. I'm going to do the same thing now with glucose. Okay, so here we have okay, so this is glucose. And we have OCO right here, thinking that the anomeric carbon. So we have OCO, yes. H is there. OH is there as well. So that is a MESTEL. Okay, so let's add another alcohol. This time, notice with glucose is a polyol. Lots of alcohol OH on there. So we can use glucose as another alcohol. Now, which OH group is going to attach? Well, which is the least restrictive sterically? Remember we had steric hindrance, unit 1? Okay, so which one of those has the most room on it, on that glucose? And let's label these carbons. In fact, let's just make it bigger too. There are 2 carbons on there that are mostly unhindered compared to the rest. Which carbons? Yeah. 6 is 1. 3 is a good guess, but it's 4. The one next to it. So those are the two OHs that are least constrained from other groups. 3 is third on the list. So what happens is we're going to use carbon number 4 OH group as the alcohol that attaches to the glucose. So none of those, all those blue ones are not going to be affected at all. So what we're going to do is this guy now is going to attach to the anomeric carbon there. That's how maltose is made. Maltose is a disaccharide. It'll be one of the disaccharides you need to know. 2 glucoses stuck together in a particular linkage. It's called a glycosylic linkage. And there's different versions of the glycosylic linkage, but there's only one that's valid for maltose. And we're going to get into that when we get into the second part of Unit 2, called an alpha-1,4 linkage. Anyway, so that's how carbs work. Carbs see each other as big giant alcohols with an anomeric carbon in it. And that is the essence carbohydrate chemistry. The problem is the structures are big and cumbersome. But the essence is just that one reaction, that acetal-ketal reaction. So let's analyze this now. So we've got OCO. We've got, is H present? Yeah, is an H there. OH, no. However, so that makes this a full-blown acetal. However, we have a second OCO because we have 2 anomeric carbons now. We have this one and on the first one. So OCO again. Is H present? Yes, right here. Is OC present? Is OH present? Yes. So this is now a hemiacetal. So maltose has got 1 acetal, 1 hemiacetal. And if a hemiacetal is present, it's a reducing sugar. I'm going to talk a lot about that when we get into carbs. Okay. How do you guys feel about this? Yeah, now ether is COC, not OCO.
But it has two carbons.
But as soon as you get the second oxygen, it's no longer an ether. That's either a peroxide or an acetal.
Why does the one on the right not have OH, but then the one on the right? So
With the OH, remember, the second glucose we're treating as an alcohol. So the alcohol replaces the OH. That's why there's no OH there. And it happens to be a carb, but it's still an alcohol. So the reactions using the OH on the glucose as treating it like an alcohol, and it is an alcohol. So that's why there's no OH there on the first as a the first carbon now. All right. Okay, and again, this is a two-way deal. So the acetal can be converted back to the aldehyde. And that's how glucose opens up. It's converted back to the aldehyde from which it came. So open, close. And the open and close reaction is hemiacetal reaction. Or if we started with a ketone and made a hemiketal, it can go back to the original ketone. All right, so three sets of reactions: oxidation, reduction, and the acetal-ketal reaction. So three, or Tim's how you count the acetal-ketal, four reactions. And it's just like unit one reaction. You have a flow chart. And the flow chart is, what I did is I added it on to your unit one flow chart. So let's see. Can I include that in here? So this is the unit two flow chart. So this down here was added. Okay, so that's basically it for aldehyde and ketone. I'm going to introduce you to carbs. Then we're going to go relax in the lab. Okay, are there any questions about aldehydes, ketones? All I can say is you need to practice these. Because in my opinion, these are not intuitive. And what they weren't for me when I first learned these. Now, when I first learned these, I took a year-long, I went to Dave, took a year-long OChem class, which was only OChem, no biochem at all. So I didn't get to carbs until I worked for a carbohydrate chemist, and it was Dr. Painter. And so that's where I learned carbohydrate chemistry from him. And he was legally blind, which to me, I don't know how the university allowed him in the lab. He was legally blind. His glasses were super thick. And he hired me to be his eyes. Actually told me that. And the first day on the job, his lab was a disaster. Where dirty dishes all over the place. It was a disaster. So he said, the first day on the job is organized. So that's what I did all day. He was a cool guy though. He was pretty elderly when I started working for him, but anyway, that's how I learned carbs. And we made, he was trying to synthesize sucrose, table sugar. And the reason why it's so challenging to synthesize is because all the OH groups are potentially a reactive alcohol. So what we had to do is we had to tie those up with other reactions and leave only one carbon 4, available. Then we were able to synthesize sucrose. Now, sucrose is made up of glucose and fructose. And so whenever you eat table sugar, it immediately in your mouth, through an enzyme called amylase, converts it to glucose and fructose. So you're essentially eating fructose when you eat table sugar. And all the ramifications of bad things with fructose come into play. Fructose is quite a bad little guy. In moderation, it works really well. It was first used with diabetics because it's significantly sweeter than any sugar, any natural sugar. Okay, so what we want to do is. Okay, so I want to go through carbs now, kind of in a generic way, without doing any reactions. Wednesday, I'm going to hit carbohydrate reactions really hard, lots of detail. Okay, as you know, too many carbs, visceral fat and subcutaneous fat is the result. For example, this is mostly visceral fat, by the way, which is the bad fat, not the less bad fat. And carbs are one of the sources of energy along with fat in our bodies, as you know. So the deal is when we consume a carb, through our biochemical pathways, say we need more ATP, adenosine triphosphate, the energy molecules. If our body says no, then the carbs go to glycogen, which is the only carbohydrate our body makes, glycogen, which is similar to starch. And our body needs ATP, it goes to the glycogen, assuming it's there, takes it apart, and then glucose starts the carbohydrate metabolism, which is 3 parts. So it's glycolysis, Krebs cycle, and electron transport, 3 parts. Okay, the deal is carbohydrates are polyols, and aldehydes or ketones, all in one molecule. Now, carbs can be little bitty things or huge things, and everything in between. Now, there are four groups: monosaccharides, disaccharides, oligosaccharides, and polysaccharides. You're going to be learning structures for each one of those. 2 or 3 for each one. Now, oligosaccharides you probably haven't heard of. Has anyone, who has heard of oligosaccharides? Anyone? Yeah. They're extremely important. Let me give you one example of why they're so important. If you don't breastfeed your baby and you feed it formula, one of the most important parts of that formula is an oligosaccharide. Well, it's called raffinose. And raffinose is a prebiotic for your baby's microbiome. Old-fashioned formulas back in the 50s didn't include that. Basically, it was sugar water. Like I was fed as a baby, sugar water. No raffinose in it at all. So my gut bacteria suffered. Hence, I had diarrhea and a bunch of stuff. But it was because my parents were uneducated regarding that. And now they always put it in, at least in this country in Europe. I don't know about third world countries, but so that's a really important one. Another one is stachanose. Stachanose is another oligosaccharide, bigger than raffinose. Raffinose is probably the simplest one. Stachanose is kind of interesting. It makes you fart. Stachanose. That's why when you eat beans, you have gas, because it's stachanose. So whenever you make beans, the best way to make beans is starting with the dry bean. What you do is you soak it overnight. Soaking it overnight dissolves the stachanose on the outside of the dry bean. And then you dump your water, which all the stachanose goes down the drain. So you have very little gas if you cook your beans that way. In my opinion, they taste better too. Dry beans, I like dry beans. Canned beans are okay, but dry ones, I like the texture, but everything's better about it. And they're cheaper too. Dry beans are extremely cheap. Pinto beans, bulk, go to Winco, you can buy bulk pinto beans for like 17 cents a pound. A pound. A pound of dry beans goes a long way. Makes a lot of beans. Okay, so anyway, there are four groups. I'm going to start with the simplest one, which are the monosaccharides, like glucose, fructose. Those are some of the simpler ones. Now, there's something that's unique about amino acids and carbs. Enantiomers exist. Enantiomer is a type of isotope that is a mirror image of one another. Pick your hand. Look at the formula for your hand. 4 fingers, 1 thumb, 1 palm. 4 fingers, 1 thumb, 1 palm. Are these the same hand? No. One's the mirror image of the other. So this hand is an enantiomer of this hand. So we refer to each one as an L or D form. Now, all the naturally occurring carbs in mammals are D form. We have D glucose, D fructose, all Ds. Amino acids are all Ls. Same idea though, mirror images. So L carbs are not going to exist in our class. So whenever we say glucose, we're referring to the D version of glucose. Bless you. Okay, another thing about carbs is they have something called a chiral carbon. The chiral carbon is a combination of attachments to a carbon atom. For example, you have to have 4 different groups to be chiral. If it's chiral, then you have the D and the L form. So if you have a really tiny carb, it just doesn't have a D or L form because it doesn't have a chiral carbon. Chiral carbon has to have 4 different groups. So look at the top one here. Okay, question is the top carbon a chiral carbon? Well, let's look at it. Okay. That's that guy there. So look at that carbon. How many groups are attached to that carbon? Three, not 4. That's why it's not a chiral carbon. Look at the bottom one. It's got 4 groups. Got 1 carbon-carbon, 2 CHs, and 1 carbon OH. Okay, it's 4 groups, but they're not different. 2 of them are the same. So we have effectively 3 different groups, not 4. So that's not a carbohydrate either. The only one that's chiral is the one in the middle because we have 4 groups attached to that middle carbon, an H, OH, and this group up here, this group down there, and none of them are the same. So that middle one is a chiral carbon. I remember one of my students was taking the MCAT test, and that question was on the MCAT test. The 4 or 5 choices were these various molecules. You had to figure out which one was chiral. Okay, and because there's a chiral carbon present, then the D and L exists. Now, if you have more than 1 chiral carbon, then you can have more combinations of D and Ls. So if we look at this guy here, this is a hexose, 6-carbon sugar. At the top is not chiral. The next one down is chiral. We're different groups. The next carbon down from there is also chiral, 4 different groups. And it goes on down the string till we get to the last one, which is not chiral. So it's got 4 chiral carbons. 4. So this guy definitely exists as a D and L. Okay, so how can you tell the L from the D? Okay, you line up the uncyclic version of the sugar, putting the aldehyde group at the top. And as you line them up, the next one closest to the aldehyde group, if it goes to the left, it's the L version. If it goes to the right, it's the D version. Now, most of the carbs are cyclic, so you have to open them up before you can figure this out. Okay, physical chemistry, physical properties are identical for the D and the L. There's a problem though. The biochemistry isn't necessarily the same. The chemistry is, not the biochemistry. Let me give you an example of that. Who's heard of thalidomide? Okay. Do you know what's associated with thalidomide?
Not at all, I've only heard the name.
The what?
I only heard the name, that's.
Back in the 60s, they used to give thalidomide to pregnant women in their first trimester to prevent nausea. They did not distinguish between D and L forms of thalidomide. One helped nausea, the other was a teratogen. Who knows what a teratogen
With defects of the.
causes? Birth defects. So one version of thalidomide caused these massive birth defects. These babies were born with no arms or legs. It was horrible in this country and Western Europe. And it was D versus L. When they manufactured thalidomide, they didn't distinguish, making sure that it was pure D or pure L. So also with, who's heard of MSG? You should all raise your hand. MSG stands for monosodium glutamate. Glutamate comes from the amino acid glutamic acid. Remember I said earlier, amino acids have D and L forms as well. They're the L forms. When you buy MSG at the store, you're getting both the D and the L forms. Some people are allergic to the D form. A lot of people are not, but some people are. And that's why they say, it causes all these problems. But only with certain people that have problems with the D form of glutamate. So D and L is around biochemically. Chemically, on the benchtop and a test tube, all the same. It's because enzymes are particularly sensitive to shapes. And it has to do with the active site of the enzyme. We're going to talk, when we get to unit 4, we'll talk a lot about enzymes. Okay. Okay, so again, the humans, mammals are looking at D isomers for carbs, L isomers for amino acids or protein. All right. When we say hexose, that means the main backbone has 6 carbons, pentose, 5 carbons, etc. Now, there's 2 kinds of carbs. There's an aldose and a ketose. Aldose, the anomeric carbon is an aldehyde, and a ketose, the anomeric carbon is a ketone. So you have the backbone number, triose, tetrose, pentose, hexose. Then you have the anomeric carbon type, ketose or aldose. For example, here we have, on the left, we have 4 carbon backbone, so it's going to be a tetrose, and it's got an aldehyde in it, so it's an aldotetrose. The one on the right, again, 5 carbon backbone, only this time it's got a ketone instead of an aldehyde, so it's a ketopentose. Okay, most monosaccharides are aldoses. So they're going to form acetals and hemiacetals because there's an aldehyde based in there. Okay, There are quite a few structural isotopes of 6-carbon sugars. Quite a few. We're only going to learn a few of them. Let's see. Okay, so these are all hexoses here. There's 1, 2, 3, 4, 5, 6, 7, 8 Ds and 8 Ls. So 16 hexoses. So we're forgetting about the Ls, just looking at the Ds. So there's 8 of them. There are 3 you're going to need to know. Glucose, galactose are the aldo hexoses. The keto hexoses, just one, to be fructose. So those are the 3 monos you're going to need to know. And all the associated reactions with those. And as far as these guys go, you need to know ribose as well. Now, as far as sweetness goes, the sucrose is a standard. And they say that's sweetness level of 1. Look at fructose, almost twice as sweet as sucrose. Now, fructose was used a long time ago in the 40s and 50s to diabetics because it was so sweet you didn't have to use as much. Because in those days, they didn't have any artificial sweeteners. Now, we're going to be looking at mostly cyclic versions of these carbs. And we're going to be using as a 3-dimensional representation on a 2-dimensional piece of paper. And they call that the Hayworth structure. So the anomeric carbons always go to the right, except in biology books. They would show sucrose with the fructose in a non-standard way. And I don't know why they do that, but they do it. Okay, so ribose is a pretty simple little sugar. And you've probably heard of deoxyribose, part of the nucleic acid series. And this is where I'm going to stop today, because I'm going to get into the reactions. I gave you a harbinger of that reaction a little while ago. So this is what we're looking at here. How these guys open and close. So, all right. Are there any questions about this stuff so far?